Hello, I'm Connor Logan, and this is my slide report on the Digital Sampling Lab. This is a table of all the required information about the unknown samples from week 2 that we were required to identify. Of particular note that's not represented well in the table is that the additional peaks of the square wave were the same as the triangle wave, but fell off in amplitude much slower. The sawtooth wave had peaks at every even and odd harmonic instead of just every 2000 Hz. In track 11, the FM wave was sweeping a peak from 900 to 1100 Hz. Moving on to my own week 3 experiment, it was motivated by the question of whether a true 4000 Hz signal and a signal of higher frequency that had been aliased down to 4000 Hz would both produce the same contribution to the power spectrum when combined with a second true 4000 Hz signal. Some background needed to understand this experiment. Waveforms are of course continuous, but the data acquisition we use to measure them is always discrete. Also, there's a special frequency called the Nyquist frequency that's half of the sampling rate of your data acquisition device. Any component of a waveform you're trying to measure that's higher than the Nyquist frequency will get aliased down. To avoid this, a low-pass filter is required to remove these high-frequency components. However, in experiments where things in the passband must be measured very, very accurately, this isn't acceptable because a low-pass filter will slightly attenuate these signals even if they're in the passband. This gets worse the closer to the cutoff frequency you are. This gives the motivation for this experiment. If an aliased frequency that's at a lower peak due to aliasing is indistinguishable from a component at that frequency that is truly at that frequency, we can simply accept the aliasing and then analytically remove it after we measure it. The equipment used for this experiment was a LabJack T4 data acquisition device, as well as a microphone kit for the DAC. In addition, there were 2 laptops. One just played an audio signal, and the other played an audio signal and ran the DAC. The procedure for this experiment was as follows. After ensuring the DAC and microphone were working, the sampling rate was set to 12,000 samples per second, and the record linked to 1,000 samples. This sampling rate was chosen because it's the rate that aliases an 8,000 Hz signal down to 4,000 Hz. A 4,000 Hz signal was then played over one laptop and the power level was observed. The same 4,000 Hz signal was played on the second laptop and the volume adjusted to match the power level of the first. Step 3 was then repeated with an 8,000 Hz signal, ensuring all 3 signals were at the same power level. The result of playing both 4,000 Hz signals at the same time was then recorded. Next, the result of playing the 4,000 Hz signal and the 8,000 Hz signal together was recorded. Finally, the power spectra of these 2 runs was compared. As for the results, the power spectral density of each independent signal was calibrated to 15 volts squared per hertz. The 2 4,000 Hz signals together produced a peak of 0.28 volts squared per hertz at a 4,000 Hz peak. The 4,000 Hz signal and the aliased 8,000 Hz signal played together produced a peak at 4,000 Hz as well. However, it oscillated between 0.15 volts squared per hertz and 0.30 volts squared per hertz. The 2 4,000 Hz signals acted roughly as expected, with the resultant power level being the sum of the 2 component power levels. However, the aliased 8,000 Hz signal did not behave the same as the 4,000 Hz signal, as it alternated between being the sum of the 2 component signals and only 0.15 volts squared per hertz. The differences in behavior can be explained by phase differences between the 4,000 and 8,000 Hz signal. The 2 true 4,000 Hz signals were always in phase, meaning the resultant amplitude was always the combination of their individual amplitudes. However, the aliased 8,000 Hz signal was out of phase with the 4,000 Hz signal, resulting in varying contribution to the overall signal power level depending on when in the 8,000 Hz signal's period a sample happened to occur. The result of this is that intentional aliasing is not a replacement for a low-pass filter, because an aliased signal that appears to be 4,000 Hz does not actually act the same as a true 4,000 Hz signal. A brief note on error: the 2 4,000 Hz signals did not completely add up to 0.30 volts squared per hertz at any point, even after allowing them to run for many, many periods, but rather only added up to 0.28 volts squared per hertz. This is likely the result of them being not truly completely constructive interference, because the two speakers playing the signals were not at the same point in space relative to the microphone. This would be a form of systematic error that can be minimized by putting the speakers as close together as possible relative to the microphone. This is the references to the digital sampling guide, as well as the reference to where I got the picture of the LabJack T4. These are my notebook pages from the lab.